Well, in this video, we are going to talk about general curvilinear motion, and that has to do with motion along a curved line. Here we see in blue the curved path and particles traveling along this path with a position of the particle as a function of time. We can draw a position vector to this thing. Let's draw it actually to the particle from, say, some point O. And then R is going to also be a function of t. So R is our position vector. Now, as our particle moves, we can track a displacement of that particle. So we move to our new position here. It'd be easier for me to move the particle than the line. To our new position here, which is R prime. Then we have a delta R between these points. And we can relate that delta R to this delta S. Which is the change essentially of our arc length as we move from, say, an S1 to an S2. So our delta S, S1 minus S2, and our new position, R prime, equals R plus delta R. We can now think in terms of velocity, where if we have a change in R over some time increment, then we can calculate an average velocity associated with that. Notice that the t here is a scalar and the r is a vector. So, of course, this will lead to us taking the limit as dt approaches 0 of delta r over delta t. And we define that as our derivative of the vector r with respect to t, and we call that our instantaneous velocity versus our average velocity. Notice this occurs in the direction of delta r, which is tangent to the curve. So also note that the magnitude of delta r approaches delta s, again, as delta t approaches 0. So this delta s is the arc length change, or the change in arc length. So our limit, let's do this in white, we don't need to be in red. The limit as delta t approaches 0, just restating this, I guess, delta r over delta t equals the limit as delta t approaches 0 of delta s over delta t. And we call this the speed scalar. And that equals ds dt equals v. Not a vector there. All right, let's switch gears to acceleration. Okay, so as our particle moves from the S1 to S2, we have a velocity moving from v to v prime. Both of those are tangent to the curve, and v prime equals v plus a delta v. But that vector combination is arrived at using a different curve. So if we take the v and the v prime here, and we set up our relationship for these, we end up with again, this delta v, but this curve is that these are following is called, has a special name. Turn the ink to shape off. Oops, turn the whole thing off. Call this the hodograph. So then our delta v over some time increment delta t equals our average acceleration and we can get an instantaneous acceleration by taking the limit as t approaches 0. Now, although this delta v is tangent to this hodograph, it's not necessarily tangent to our path. That's important because that's the direction of our acceleration. Okay. So, summary, since v equals dr dt, let's make this a lot different than that, v dr dt, then our acceleration is the second derivative of this, d2r dt squared, and acceleration tends to pull or swing the velocity towards the concave side of the curve. Or in other words, the acceleration points inward.